Hello. In this lesson, we're going to talk about the entry quiz to calculus. So now you are at the gate into calculus. Have a very well prepared algebra background will help. And if not, it's going to be, you're going to have to catch up along the way and do the best you can. And the first question, okay, I wish you to look at this, look at the quiz on your Canvas site. And I'm going to put this on the side we're going to be showing you the work and explain to you the related concept that you need to study. And where you can watch that in the Canvas side, and and the similar topics you can find in the textbook. The first question, entry quiz to calculus. Hold on. Quiz, entry to calculus. Okay. The first most common mistake is that if X is any real number, okay, then, the square root of X squared equals to X. We know that this is false. The reason it's false it is because when X is negative, it will make a false statement, right? So we have a counterexample. The counterexample, if you pick up any number, which is a negative number, you will find that the left-hand side would be equals to the square root of -1. And that equals to the square root. By order of operation, we'll do the -1 squared first. That's going to be +1. And the right-hand side, the square root of 1 is +1. And the right-hand side is going to be -1. And obviously, +1 does not equal to -1. Therefore, this statement is false. False once it is false. So in this one case, so we pointed out the case that the statement is false, okay? That is, okay? When X equals to -1, it is false. This statement is a false, okay? Thus, that statement is a false. False once false. Okay? So mathematical statement, it's true, always true, false once false. Okay? So mathematical truths okay, true always. False once, false. Any statement that's false once, it doesn't have to be false. You don't have to point out many more times. You just one time how false is false. Okay, second question. And this is yet another very common mistake. Very common mistake. So P plus Q squared. You probably learned this in elementary algebra. Okay, P squared plus Q squared. It comes with different shapes and forms. Okay, sometimes it's X plus Y squared, and another time, it could be capital A plus capital B squared. It's all similar statement. Okay, So this is a false. Since we didn't indicate what kind of numbers PQ are, so PQ can be any real number. Okay, PQ can be any real number. If not specified, it means it can be any real number. Okay, and this is false. Why it is false? We also could come up with a counterexample. Okay, so we have a counterexample. So we want to specify that false ones. Okay, so many examples. You can have A equals to 3, B equals to 4, right? And 1, 2, it all works, right? Just have to have a one case of falsehood for the left-hand side. The left-hand side is 1 plus 2 squared. Okay, so 1 plus 2. And that equals to 3 squared. And 3 squared is 9. And the right-hand side is p squared plus q squared. Right? So that's 1 squared plus 2 squared. And that's going to be 1 plus 4 equals to 5. 9 is not equals to 5, right? So we have identified one case, that statement is false. Okay? False ones, false. False. Okay, so I hope you guys mastered this technique of explaining why certain statement is false. Okay. Number three, it is a true statement. It is a true statement. And of course, we do this in the domain of square root of A times B is equals to square root of A times square root of B. Okay, and so this will be related to a function, right? So of course, in this case, we assume A and B are from the domain of the function square root of f of x equals to the function which is square root of x. Okay, so this is a function you can relate to, but that is a true statement. Okay, so the kind of value we implied about A and B is that A must be in the domain, which is going to be greater than equals to 0, and B is greater than equals to 0. And the reason we can infer that is because the function, the domain for this function is x greater than equal to 0. Okay, the domain of the function, right, is x is greater than equals to 0. That's how it's being related to. Number 4. Square root of A squared plus B squared is equals to A plus B. It is false. Why it is false? Well, you just have to have a counter example. You can just have to have a counter example. Okay. First, say we have A equals 3, B equals to 4. I want you guys to understand why these statements are false with concrete examples. So you will not be making those mistakes. Okay. So in this case, when A equals to 3, B equals to 4, the left-hand side is 3 squared plus 4 squared, and then take square root. So according to the order of operation, we have square root of 9 plus 16. And that equals to the square root of 25. The square root of 25 is 5. And the right-hand side is a plus b. So that's 3 plus 4 equals to 7. Right? So apparently 5 is not equals to 7. 5 is not equals to 7. Okay, not equal to. Thus, okay, so that statement, this statement is false once, so it's false. False. Okay, so that's how we make this statement. I hope you guys, when you're about to do this, think about, could there be a counterexample? Okay, so number 6. Oh no, number 5, sorry. Number 5. Number 5 is another common mistake. Okay, so 1 plus t times c equals to, over c equals to 1 plus t. Okay, this mistake, this kind of mistake actually show up in many shapes and forms, right? This, for example, you may have an example like this, right? You may have an example, say 1 plus 2x divided by 2. Right? Then you say, hey, that's equals to 1 plus x. Wrong. Okay. Well, this is wrong. Okay, so let me just be a little bit dramatic so you remember what will be right. In what case you can cross out the 2, right? If you have 2 plus 2x divided by 2, in this case, you factored out the 2 on the top, so you get 1 plus x, 2 times 1 plus x divided by 2, and then you have 1 plus x. So let me make the font a little bit larger, okay? So in this case, you see the difference? The difference is that here you have 1, you cannot factor out a 2. And in this case, yes. And we can easily give counterexamples. Okay, counterexamples. So you can make many counterexamples in your situation, right? Counterexample is a very powerful tool. Okay, so you can use this one as a counterexample. T is, T is 2, right? And you can use concrete numbers. You can use concrete numbers. I can use T equals to 3, right? C equals to 5. I'm just randomly picking up numbers. Can you pick C equals 0? No, C cannot be 0 in this case. Okay, so your left-hand side would be T is 3, right? C is 5, and C is 5. So in this case, you have, according to the order of operation, 1, you do the multiplication first, right? And that's 1 plus 15, and that's divided by 5, and that's going to be equals to 16 over 5. Right? What's on the right-hand side? The right-hand side would be 1 plus t. 1 plus t. T is 3. 1 plus 3 is 4. Right? Obviously, these two numbers cannot be the same. Okay? 16 divided by 5 is less than 4. Okay? Not equals to 4. Right? So one counterexample. So if false once, false. Okay, so many different cases of similar nature that we might make these mistakes. So do not make such mistakes. Okay, so this example actually is a, it's a condensed form of similar mistakes. Okay, number six. 1 over x minus y equals to 1 over x minus 1 over y. It looks very intuitive, but it's a terrible mistake. It's a terrible mistake. Okay? And we know that it is false. Don't get there. Don't get there. Counterexample. Counterexample. As long as you don't take x equals to y, because you're going to make a zero denominator, that'll be fine. Right? Suppose I choose x equals to 3, y equals to 2. Okay, I'm just picking up some random numbers. On the left-hand side, it's 1 over x is 3, 3 minus 2. That's the left-hand side. And that equals to 1, 1 over 1, right? 1 divided by 1. Order of operation, you do 3 minus 2 first, and that equals to 1. The right-hand side is 1 over 3 minus 1 over 2. Well, you can do some operation, but you don't have to do any operation because 1/3 is smaller than 1/2. This number is going to be negative. A negative number certainly is not going to get equals to 1, right? So that's one perspective. You have already demonstrated it's not. But if you insist on getting a number for it, right? Say, oh, I really just want to see what it is. Well, go ahead and find common denominator. Okay, so what will be the common denominator? What will be the common denominator? 1/3 and minus 1/2. The common denominator will be 6, right? So how do we get that common denominator? We multiply. We use principle number 1, 2 over 2, right? Multiply 1, nothing changes. Any number times 1 stay the same. 3 over 3. So you found the common denominator. And then you have 2 over 6 minus 3 over 6. Oops, 3 over 6. And then you get a negative 1/6, right? Negative 1/6 is a negative number you're getting. Certainly is not equals 1, right? All right, so we have that false ones case, right? So these two numbers are not the same. So they're not the same, not equal. Okay, so once again, false ones, false. Okay, number 7. Number 7, okay. During the lesson, anytime you can pause. You can pause the lesson and or rewind, and then just do some work on your own. 1 over x and a over x minus b over x, right? So let me make fonts larger so that hopefully will help you see better. Is this true or false? Right? Assume that we don't get denominator, we don't get, zero denominator. If that's guaranteed, we look at the left-hand side. Okay, let's do some algebra. We have the left-hand side. On the left-hand side, we actually, if you look at the denominator, it has a common denominator, okay? So we could apply the common denominator and do a minus b, okay? So the denominator would be equals to a minus b divided by x. Then if you multiply x on top, x in the bottom, assuming x is not 0, x cannot be 0, then you multiply 1, anything times 1 stay the same. So 1 times 1 over x equals to 1 over x times x. Denominator multiply x. You can see x and x will reduce. So as a result, we are getting 1 over a minus b. So this is a true statement. This is a true statement. This is true. Number 7, done. Number 8. Okay, number 8 says if f is a function, okay? Function is a huge word. This word implies many functions you have learned before. Many functions before. Okay, so here I wish to just review some of the functions we're going to use very often. Okay, so in this course, we're going to use some of these functions. We're going to use these functions and all kinds of combinations of these functions. Okay, example of functions. Okay, first, what is function? Definition. We spend the entire semester in all the courses from, pre-algebra, which prepare us to get to pre-calculus. Okay, in pre-calculus, we covered all the functions together. Okay, so we know that a function is a rule that assigns each input exactly one output. Okay, let me put them in one row. So there's we have this rule. Okay, we have a rule, and this rule takes the input. Produces output. Okay, so let me change to a nicer looking arrow. Okay, the rule is the function, but the rule says that this rule called function is not any rule. This rule has to produce exactly one output for each input. So input has a category, it's a category of itself, and output has another category. You can imagine there's multiple inputs and there might be multiple outputs. So the input, if all the possible input make domain, okay? So the input are from domain. Okay, so let me find the symbol. So the input are from something we call domain. You must have heard that before, right? Output belongs to all the possible inputs together, we make domain. All the possible outputs, we call them range. Okay, and that's what the rule is. Okay, every function has a domain. every function has a range. So now the rule is a function. Okay, so we're gonna we're gonna give a name. Okay, so that's the situation. What are the functions we have studied, right? And we talk about a function that's equals to a constant. It means that no matter what's the input, the output is always the same, constant. Okay, and so I'm going to give you a group of functions that you have seen before. F of x, okay. All these are rules. Output is the same as input, right? Output is the square of the input. And all of these functions you get to use. Okay, and we have studied the other function, which is the absolute value function. Okay, regarding absolute value function, we have some sections that I wish you guys to go over. Okay, so let me show you where it is. Hold on. Did you see that? Hold on. Wait a second. Okay, absolute value function. Okay, on Canvas. Absolute value function right here. Okay, right here. About 40 minutes of lesson. Okay, 40 minutes lesson. So please watch that. We did it in class. Very important function. It can easily give you or take away 20, 30 points from your work on quizzes or exams. And more functions. Okay. These functions, I coined the word basic functions, root function, right? We're gonna use these functions in this semester. Okay, and what else? Absolute value, constant, we should have 8 of them. 1, 2, 3, 4, 5, 6, 7, cubic root. Okay, another function with 1 over x. Okay, these functions, they're all covered. Okay, so let me get to Canvas. These functions are covered here. Review functions, x cube functions, reciprocal functions, root functions, property of absolute value, which you can study this with absolute value function. Okay, root functions. Okay, so this is these about this basic functions. All 1, 2, 3, 4, 5, 6, 7, 8. These 8 functions we're going to use. You're going to use them in calculus classes, not only in Calc 1. You're going to use them in Calc 2 as well. Okay. So now another subcategory of functions that is going to be f of x equals to exponential and logarithm functions, e to the power x. Okay, you're going to use them all the time. ln x. Okay, in calculus, you're going to use e to the power x and ln x. But to get you guys familiar with it, let's go back to the lesson. Okay, exponential log functions, base e. Okay, it's being extensively studied. I also have lessons on base 2, base 3, base 10. But but those are, you know, other lessons. I hope you don't need it. Just go straight to exponential function, e to the power x, ln you know, and log, common log functions. I'm sorry, natural log functions. This lesson will get you, you know, oriented. We'll review these 2 functions. Okay. Now look at the trig functions, right? Look at the trig functions. So now all the trig functions, right? All the trig functions. What are they? Sine, right? Cosine, tan, cotan, secant, cosecant, 6 of them. Okay, arcsine, arccosine, arctan. Okay, these functions are reviewed in these lessons. Sine. Okay, what's important about them? Arcsine, composition, sine, summary, cosine, tangent, arctangent, all of these compositions. Okay, you need them. Okay, you need them. And exponential logarithm. Okay, exponential logarithm. I'm going to bring these back, exponential logarithm properties, and to bring them with the exponential logarithm, those properties, and the common mistakes in logarithm. Okay, the common mistakes in logarithm can be seen. Okay, before, I hope you review these materials so you don't make those mistakes. Okay, so bring these three together to study them. It may take you, 3 hours, but you really have to take notes and work on it so that you know, I know this is a lot because this is the 7 courses before calculus. That's the foundation. Okay, that's the foundation. And next, piecewise function. Okay, we've done some piecewise functions in classes, but we're going to be using a lot of them. Piecewise functions. I have 2 lessons, more than 2 hours of explanation, many examples. All of these examples that you see in my lessons here, they are mostly from calculus text. You are going to encounter them. Okay, so just remember where it is. You may or may not have to see them. You may not to study them now, but we will get to them. Okay, so all of these functions and their compositions, including piecewise functions. We actually saw some piecewise functions, right? The absolute value function, the way we wrote it down, that's a piecewise function. Okay, so I'm going to show you what we wrote down in class, so you've seen this. Okay, the absolute value, a non-negative number, if x is greater than or equal to 0, is the same as the number. If x is negative, the absolute value of a negative number is its opposite. We saw how many ways we can tweak them, right? Now, this function, and there are many similar functions, this is called piecewise function. There are 2 pieces, right? So if you graph this function, you see there are 2 pieces. Of course, we're pretty familiar with this form. Just to remind you, there are all these pieces. That's why it's called piecewise function. We're going to be using these functions. And all of these functions are simple functions. And we can make them complicated, can we? Okay. So many such basic functions, right? So in the statement of 8, right? F is a function. That statement implies what? All of these functions are included and more, because from these functions you can produce, how many functions can we produce? If you look at the operation of functions, right? If you look at, so here I'm writing down, these are examples of basic functions. basic functions. From these basic functions, right? From the basic functions, okay, we choose any function arbitrarily. Okay, one is called f, one is called g. What can you do about them? Right, you must have learned this before. You can do f of x plus g of x or minus g of x, right? You can also do f of x multiply. You make new functions, and you can also do f of x divided by g of x, right? Provided, no zero denominator. So you add, subtract, multiplication, division, so you're going to produce more functions, including piecewise functions. You're going to produce many, many more functions, and they are all included in this short statement. I hope you understand that. Okay. Now, there's another making of function is called a composition of functions. Composition of functions. We're going to use this in chain rule. Some of you who have taken calculus class, you know chain rule. Chain rule might mess up a lot of people. Okay, chain rule is just a topic that is pretty intense. It's related to compositional functions. Okay, so what it does is you have f of g of x, and you can have many, many layers. Okay, you can have many, many layers. You can do f composite f, you can keep going forever. And the g, right? Think about the possibility. And you're going to make even more functions. You can make even more functions. Just keep going. Okay, how many layers? Who knows? Okay, as many layers as you want. All of these can produce new functions, and all of these new functions are included in this statement if f is a function. And then it says, well, what does this mean? S is input S plus input T. Okay, so what does that mean? It says for any function you made, right? We have input S plus input T and use it as input for the function. The output is f of S plus T. Okay, so that's the left-hand side. The right-hand side says if you have S, apply the rule of the function, it produces f of S. Okay, and you have a T, apply the rule, and you get the output of f of T. So this statement says, if you produce f of S plus T this way, on the left, on the right-hand side, if you just give input to f respectively, you add the output, and they're going to be the same. Then, if this is true, right? We talk about mathematical truth. Truth has to be true all the time. And then you start to question, is this true all the time? Is this true for all of these functions? All of these, one by one, right? If you verify all of that, and all of the possible functions you can think of, if that's all true, then maybe it is true. Okay, but along the way, we realize, what do we realize? Wait a second, f of x equals to x squared, right? If we apply this rule to this specific function, right? What would this be producing? This will produce s plus t squared. And what would this be? This will be s squared. And this will be t squared, right? So for this rule, okay, I pick out a function for this rule, and we just mentioned, right? P plus Q squared, where was it? We had it over here, right? If this is a false, would that imply that s plus t, s squared, t squared is false, right? It's false. Therefore, if the statement is a false one, a false once, so the statement is what? False once, false. So this statement is what? False. You need to understand the implication. We need to understand the implication. Okay, so that little statement, that little if condition implies function f can be any function. Okay, any function. We need to understand that scope of that question. Okay, so let's keep going. Right? We see the you know, how much function this function concept includes. Okay, and we are studying these functions in calculus course. Okay, for me, I taught calculus. I taught pre-calculus last semester. Okay, I always have, you know, calculus in my mind when I'm teaching that. Okay, so let's look at number 9. Number 9 says, if, right? So now you know when we mention a function, it implies, you know, you have to refer to the definition of function, right? You have to refer to any such rule will be called a function, and that's included. So this statement says, if, okay, let me change the color. If, obviously, function f of s equals to f of t, then s equals to t. What does that imply? It implies that we talk about st, right? Okay, let's start from here. Okay. Each input has exactly one output. That's a function. So when the output are the same, does that imply the input must be the same? And that is true for any function, right? Then you start to think. When it is true, when it is not true. Certainly it's not true. But other cases, it is true. Right? For example, if I use the function f of x equals to x squared, right? It will give me st. For example, my s will be 2, my t will be -2, right? So in this case, f of 2 equals to 2 squared, right? And f of -2 equals to -2 squared. Both equals to 4. They have the same output. But can we say 2 equals -2? Obviously not, right? So this counterexample tells us this is not true. But if you look at all of these functions, right? All of these functions we have just studied, basic functions, right? Sometimes it's true, sometimes it's not true. In fact, in case it is true, we have already used it in some of the cases, okay? When these two, for example, actually they're true for exponential function and logarithm function. In your previous experience, you have used this property. You have used this property. You have used this property, okay? But in some other cases, it is not. For example, if I know, right? If I say, okay, if ln x equals to 2, then I can infer then x will equals to what? X will equals to e squared. So in this case, we use this property. We use this property because 2 is equals to ln e squared, right? The output is same, therefore the input is same. In this case, the statement is true for certain functions. And in fact, you have used them before. It's also true for e to the power x, because these functions are monotone functions. What are monotone functions? Okay, they're either increasing or decreasing. And both of these functions are what? They are increasing functions. But if a function is increasing in its domain or decreasing in its domain, this will be true. However, not true calls for many functions. Okay, such as trig functions. We'll talk about that example, right? F of x equals to, say, we use sine x in class. Let's use tangent x. Right? Is that true? Okay. It's true. So I'm going to leave this example for you. Okay. Find, if tangent A equals to tangent of B, right? Can we say A equals to B? Can you see that? Obviously not, right? We know we cannot. But could you please find a counterexample like we did before? Okay, we've given many counterexamples, so you can try this, okay? I'm going to leave that for you. You have a little homework there. The other property, let's look at number 10. Number 10. If f is a function, then, right? If f is a function, then f of 3 times x equals to 3 times f of x. This is a little tricky, but wait, let's first try to understand what it means. Right? With all of those functions we have in our mind, what does it mean? Can I just pull it out? And this case show up in many different shapes and forms. For example, we have sine, we see this all the time. It's a terrible mistake. It's a terrible mistake. But we see this mistake all the time. So this mistake is compacted. Of course, now you know it's false. False one, false, right? So this is false. But we see this being done in students who are taking calculus class. What is true about sine double angle? It equals to 2 times sine x multiply cosine x. That is true, okay? So don't forget to review your trigonometry because we're going to soon use trig functions. We're going to be using trig functions. All right, so this is a false. This is a false. So this mistake is made very often. This is just it's just one of those very common mistakes. 11 is a definition of increasing function. Say if f is a decreasing function, and x sub 1 is less than x sub 2, then f of x sub 1 is larger than f of x sub 2. Okay? This is a definition of a decreasing function. This is a definition of decreasing function. Number 2, you can compare this definition with your calculus text definition. I'm not going to expand this, but we're going to cover it. We're going to be using this in chapter 2. In my lessons, I actually have lots of discussions about examples of increasing function, decreasing function. In those lessons I just mentioned earlier. Okay. So number 12 is that if a function is a decreasing function, I'm going to just take a shortcut. Okay. Increasing is an increasing function, then this is going to be reversed. Okay, so these 2 statements are correct. Okay, correct. In fact, you're going to be using these 2 definitions quite a lot. Number 13. Okay, number 13. If f and z are functions, so now we're looking at a composition, right? So we look at a composition. F and z, right? If f and z are functions, what can they be? It can be all of these and many compositions that made of, any function you can think of. Okay, you're going to see a lot of interesting functions in this course for sure. Okay, so f composite g is g composite f. Is that true? Very general statement. So f and g can be any one of those functions, right? So you can see this is not going to be true, right? Easy. Say I have f, I'm going to make f, let's do some functions with e to the power x. Okay, and g, I'm going to make it g of x equals to cosine x. What is f composite g? F composite g of x equals to f of g of x, right? So you may like to take this opportunity to look at a composition and decomposition. Okay, I'm going to point to which video you like to watch. Okay, so f of g of x cosine x, and that's going to be equal to e to the power of, right? To the power of cosine x. You might encounter this function, okay? G composite f of x. What would that be? Right, so that's g of f of x. Right? So that's going to be g of f of x equals to e to the power x. And what would that be? E of e to the power x is going to be cosine e to the power x. Are they the same? Are they the same? No. Right? They're not the same. So this statement is what? False. False. Okay. Number 14. Number 14. If f is a one-to-one function, okay. If f is one-to-one function, one-to-one function has inverse, okay, the inverse is unique, then f of inverse equals to 1 over f of x. What is a one-to-one function? I'd like to take this opportunity to review what is a one-to-one function. Okay, one-to-one function has its own precise definition. So I'm going to bring it up. So earlier on, we talk about function, right? A function is a rule. So one-to-one function has to be a a function first. If it's not even a function, we don't even talk about one-to-one function, right? So first it has to be a function. So f is a one-to-one function. There are additional requirements. One-to-one function. Okay, what are the additional requirements? One-to-one function. Okay, it says whenever the inputs are different. Okay, whenever the inputs are different, the outputs are different as well. Okay, so whenever the inputs are different, the output are different. Whenever x sub 2. Okay. And x1, x2 are from, so x sub 1, x sub 2 are from a specific interval, okay, because you can define one-to-one function, as you need, okay, from an interval where the two functions are defined. The two function refers to a function and its inverse, okay, from an interval. Okay, so forgive my English. All right. Now, whenever, so for any one-to-one function, it has inverse, right? So what are the functions that are inverse to each other, right? We know that f of x, if you look at my lessons, we know that f of x equals to e to the power x. Its inverse is f inverse is ln x. Okay, this pair of function you get to use all the time, right? And they each have their domain and range. They each have their domain and range. What's the domain? What's the domain for e to the power x? The domain for e to the power x, right? All real numbers, negative infinity to positive infinity. Okay, that's where x is from. And the range, e to the power x, is always positive, right? We studied those. Always positive. Okay, how about for inverse? Okay, so I'm going to bring this separately. Okay, and what's the domain? Domain for this function, x is greater than 0, right? So I can just remove that, not necessary. The range for ln x. Okay, so please study those lessons if you've forgotten. Very important function you're going to use for calculus classes. I'm using plural, calc 1, 2, 3. These two functions are super important, super important. Now, so let's look at this statement, right? This statement says f is one-to-one function. Yes, they are one-to-one function. And it says f of inverse. Okay, does that fit in? F inverse here is ln x. And over e to the power x, e to the power x. Is that true? Is that true? It can't be, right? So that's what it is. That's what the statement is saying. Okay, of course this is false. We can easily get a number. We can easily get a number to tell you it's false, right? Say for x equals to 1, right? We pick, not only they have this domain issue, right? The domain on the left-hand side, the domain is a positive number for ln x. The domain for 1 over e to the power x, this is equals to e to the power negative x, right? So this domain is all real numbers, and this domain x has to be positive. That's a mismatch, right? So this is terribly false. And we see this mistake in other forms, right? We see this mistake in other forms. So before we see the other forms, you can see when when x equals to 1, ln 1 equals to what? Equals 0. And what is e to the power of negative 1? Right? What does that equal to? It's 1 over e. How can they be equal? Think about it, right? So whenever you're about to do this, think about it. This is a terrible, horrible mistake. Terrible, horrible mistake. There are all these concepts involved in the process, you guys. Okay, there are all these mathematical concepts that are involved in this process. Okay, another common mistake we saw, right? This mistakes show up in different shape and forms. And some people would just write, oh, sine inverse. And this is a classic mistake. Okay, it's 1 over sine. Oh, what a terrible mistake. Arc sine. I know this notation may cause a problem. Okay, it's arc sine equals to, arc sine is the same as this piece. Okay, this is the false. And this is true. This is just 2 different notations. Okay, this is the classical notation. But these days they're replaced by this notation. So they mean the same thing. Okay, the domain for arc sine. Okay, if you have studied trigonometry, right? the domain for arc sine, right? What is the domain? The domain is this input has to be between -1, +1. And what is the range? The range, okay, which arc sine is going to be, right? So I'm going to take the whole thing because they're the same. Okay, it's going to be greater than or equals to -pi. So watch those lessons, and I have it over in Canvas, and smaller than equals to pi/2. Right? How about the domain and range for 1/sine? Right? 1/sine is what? Is a cosecant, right? Domain for 1/sine. So all these are common mistakes, right? So really just a cosecant x. What is the domain for 1/sine x? The domain for sine is all real numbers, but now sine is in the denominator, right? The denominator cannot be 0, right? Sine x cannot be 0. And what will lead to? What will make sine x equals 0? X cannot be what? X cannot be what? A pi, right? A pi. If you look, what are the values that cause sine equals to 0? Those are the values that sine cannot be. You just look at sine curve, right? Everybody should know sine curve by this time, yes? If not, please study my lesson on sine curve. So what are the values that cause it equal to 0? 0, pi, 2 pi, -pi, and so on and so forth, right? So that's their multiples of pi, and k is any integer, right? So from that comparison, you can see the domain and ranges already have a mismatch. Okay, so this is a terrible mistake, terrible, horrible mistake. Okay, misunderstanding. All these concepts are involved. All these concepts are involved. Number 15. I know this is a lot, okay, because these are concepts that has ranges from 7 courses, okay, before calculus, which makes the foundation. Okay, number 15 says you can always divide by e to the power x. This is true. Why? If you notice, I just mentioned when we talk about the domain of e to the power x, right? When I was teaching pre-calculus and when we reviewed these topics, I said domain range, right? In one sentence, e to the power x, right? If you just remove this, okay, combine them, that is true for any real number. Okay. When we talk about mathematical principle number 4, okay, maths principle number 4. What does number 4 says? If A is the same as B, then A times C equals to B times C. Of course, you can divide by C as well, provided that C cannot be 0. Right? As long as C is not 0. Now we have e to the power x is positive. It's positive all the time. So this condition is satisfied. Therefore, we can divide or multiply by e to the power x anytime. Okay, so not only you can divide by it, you can also multiply it. Okay, so this is true. Okay, number 16. Number 16. Number 16 says, if 0 less than a less than b, then, oops, sorry. Then ln a is less than ln b. That's interesting. Okay, we just studied ln x, right? So let's bring it back to us, right? Domain range. What kind of function is this? What kind of function is this, right? So please study that lesson about exponential and logarithm function. A very, very important function. Okay, very, very important function that you're going to use. Okay, all the way to exponential differential equations, linear algebra. If you're taking those courses, you're having those, right? Otherwise, you're going to be using these functions in calculus series. Domain and range. What kind of function is this? It's an increasing function. It's an increasing function. Increasing function, right? By definition, within number 12, increasing function. When input 1 is less than input 2, their output will also have the same relationship. So this is true. This statement is true. Why it is true? Because ln x is an increasing function. Increasing function will satisfy. Okay, so I'm bringing up number 12, right? You can see all of these are related. All of these are related. So for increasing function, that is true. That is true. Okay, so a and b, a is x sub 1, b is x sub 2, and they are in the domain, and that's true. Okay, that is true. Okay, if you have more questions, please don't hesitate to reach out to me. I hope this explanation is enough. Okay, if it's not enough, let me know. Okay, so finally we come down to more on exponential logarithm properties and so on and so forth. Let's look at number 17. 17. Okay, 17 says x is larger than 0, and there's of course there's the if x is larger than 0, then, right, ln x inside parentheses raised to the power 6 is equals to 6 times ln x. Okay. Okay, is that true or false? What does that mean? Right? What does that mean? It means it's a power definition. It means you multiply ln x 6 times. 1, 2, 3, 4, 5, 6. What is 6 times ln x? It is ln x adding ln x, adding ln x, adding ln x, adding ln x, adding ln x. How many times? 1, 2, 3, 4, 5, 6. Are they the same? Of course they're not. Of course they're not. You can easily come up with counterexamples. Okay, so this is false. Not only it is false, it is also a terrible, horrible, extremely bad mistake. extremely bad mistake. You might be thinking, what will be true? Well, this is not true. A 6, there are some truths to it because this equals to ln x raised to the power 6. Okay, that's a logarithm property. Okay, this is true. Okay, power rule. So I encourage you guys to study the logarithm exponential properties. So let me bring this back here, right? Go back there. So logarithm exponential properties right here on common mistakes. Actually, if you look at the common mistakes, the rest of the questions about logarithm, it will all be resolved. But here I'm just repeating what I did before. So let's get back to, because I promised I'm going to cover all of the questions here. Okay. So let's do it. Number 18. Okay, you can see these are very confusing, right? So they're different. So there, when you get down to it, that's how you see the difference. Okay. If you have more questions, please don't hesitate to reach out to me. Okay. If x is larger than 0, this is number 18, and a is larger than 1, then ln x divided by ln a is equal to ln x over a. Okay. This is one of those terrible, horrible, extremely bad mistake, which confuses change-based formula with the quotient rule. Okay, with the quotient rule. All right. False. Okay, I'm guessing the mentality of people who make such a mistake might be, okay, I'm only just guessing, okay, is that, oh, we have an ln, so we just condense into 1. It's shorthand notation. Unfortunately, this is gonna get you, you know, to a point of losing points. Okay, the latter is equals to ln x minus ln a. The former is just if you want to write it in 1, you can only do the change of base formula, which is usually you don't need to use change of base formula, right? You can see they're different. They're very, very different. Now, let's use a counter example. I think it will be better explained using a counter example. Okay, counter example. When you see the concrete number, we're going to pick number x and a from the category specified, right? X must be greater than 0, a is greater than 1. So how about I choose x equals to 1, right? And I choose a equals to e, right? If I do that, what will happen on the left-hand side? The left-hand side equals to ln 1 over ln e. We know ln 1 equals 0. Ln e equals 1. 0 divided by 1, that's 0. And what's on the right-hand side? Ln 1, x is 1, and this is E. What does that equal to? Equals -1. 0 does not equal to -1, right? So we have a counterexample. So 0 is not equals to -1. So false once, false. Okay, this is a very common mistake. It shows up in many shapes and forms. Okay, examples I have seen, right? People would do this. People would do ln a plus b over ln a minus b, and they're gonna write it as ln a plus b divided by a minus b. You see, similar mistake. Okay, so these mistakes show up. Example of mistake. Okay, so number 18 is covered. Let's look at number 19. I think this lesson is rather long. Okay, number 19 we already pointed out. Okay, sine of 2x. Very common mistake, very unfortunate. Okay, this is false. Okay, what is true? If you look at double angle formula for sine, is that sine of 2x equals to 2 times sine x multiplied cosine x. Okay. 20. Tangent inverse. I always like to call it arctangent equals to 3 pi over 4. Okay. I'm going to give you a short explanation. The short explanation would be that the domain and range for arctangent, right? Tangent inverse is really arctangent. They're the same thing. Okay, this is a classical way to represent it, and this is the modern way mathematicians are using this notation. I know the notation is confusing, but you need to understand tangent inverse is arctangent. The domain and range are spelled out. Okay, the domain is all real numbers. The range, okay, I'm going to show you a picture. Just 1 second. The range is between, okay, the range is between, I'm going to show you multiple forms of the range domain thing. Negative pi over 2 to positive pi over 2. And you're going to use this function in calculus classes. Okay, so this is arctangent curve. Arctangent curve. And these two, there's a horizontal line. One is, so I'm going to draw the, whoops, it should be negative pi over 2. Okay, there are 2 horizontal asymptotes. And another one. Okay, so the domain, if I can show you some other notation here, right? The domain is a horizontal, right? Wait, I should be using a different color. Okay, I'm going to use a red color because domain is we're using the red blue. Okay, red blue. It's a horizontal span. and the range is the vertical span. Okay, you can see the curve is between negative pi over 2 to pi over 2. Okay, if you forget about this, you need to study this and study the lesson I have for arc tangent. We have a lesson that's being posted. Okay, domain and range, right, for arc tangent. Okay, so now 3 pi over 4 is outside the range. Okay, so it's wrong. And what is the argument? Well, 3 pi over 4 is outside the range of arctangent. This is the most powerful explanation. Then you say, oh, how come tangent 3 pi over 4 equals to -1? Well, that means you need to watch the whole lesson of how arctangent is made. Okay, so I'm going to try to not make this lesson too long. So if you have that doubt, then you say, if you have a question, say, but, right, tangent 3 pi over 4 equals to -1. Why couldn't I just make this? If this is your argument, right? Why not? Then please watch the lesson on the making of arctangents, because I don't want to make this explanation too long. Okay? And if you have any questions, I'll be happy to discuss with you. Now, number 21. Number 21. Okay. Number 21 is also a common mistake. Arctangent equals to arcsine Okay, so maybe let me make the fonts larger. Oh God. Okay. And the student might be thinking, tangent x equals to sine over cosine. That is true. That is true. Right? But the inverse function, however, don't have such a relationship. So this is false. And this is true. Okay? This is a terrible, horrible mistake. You can analyze from domain's perspective, or you can just use that. Let us use a simple example. Let us use a simple example. Okay? A counterexample. When you try to do this, I hope this, because this counterexample will serve you when you're about to make that mistake and say, wait a second. Okay? Let's see. We're going to try a couple numbers, right? And they have to be all in the domain of these functions. Okay, they have to be all in the domain of such functions. And what's the domain for arctangent? All real numbers. What's the domain for arcsine? Between -1 to +1, right? So before we do that, we need to clarify a couple of things. Arctangent, domain and range, right? We have that clarified. Some of you might realize you have a lot to study, don't you? I mean, 7 courses before this course, okay? So the arctangent domain range, okay? What's the domain range for arc sine. Okay, that's arc sine, right? What's the domain? The domain is from -1 to +1. In other words, this x has to be between -1 and +1. And what is the range? Range. And the range is arc sine is going to be between -π/2 to +π/2. Okay. Now let's look at arc cosine. Arc cosine. Okay. Arc cosine. Okay. Domain the same as arc sine. The range, however, okay, is between 0 and pi. Okay, if you have any issues with these questions, go watch those lessons. Okay, those lessons have explained in details about these issues. Okay, and you must know. All right, so now we want to come up with a counterexample, right? So the x has to be in domain for all three. Since the domain for tangent, arc tangent is all real numbers, and the domain for arc sine, arc cosine between -1 and 1, so we just have to look at the common part, right? It has to be in the domain of all three, okay? So let's look at a then we're just going to choose a number in between, right? Let's try to make it easy. Try a couple numbers. X, how about x equals to 1, right? Make it easy. And arctangent of 1 equals what? Equals π/4, right? Arctangent of 1, what would that be? Arcsine of 1, what would that be? It's π/2, right? And what's cosine, arc cosine of 1? Arc cosine of 1 equals what? What does that equal to? Equals to 0. And we are running into a problem because look at 1 is going to cause what? We're going to cause the denominator equal to 0. So this is not going to work. Okay, let's choose -1. Right? Let's choose -1. -1, -1, -1. Okay, we know this is not going to work, right? I want to give you an example so this is going to be -π/4, and this is -π/2. Cosine negative arc cosine -1 equals to pi. So now let's check if this is true. Okay, so on the left-hand side, tangent of this -1 that's going to be equals to -π/4. And what's on the right-hand side? What's on the right-hand side? The right-hand side, is dividing, right? Dividing. So this is going to be -1, okay? And this is the -1. Okay, make the font larger so you can see the negative sign. Ooh, look at what we're getting. Look at what we're getting. Sine, arc sine of -1 is -pi/2. Okay, if you have any questions about that, go watch the arc sine lesson, okay? And this is pi, right? This is pi. And if you reduce this, what do we get? We get -1/2. Is -pi/4 equals to -1/2? So this will be the good counterexample for you to practice, okay? So that you know you don't rush to make that mistake just because you know tangent x equals to sine over cosine, but does not mean arctangent equals to arc sine divided by arc cosine. Okay, so don't make such a mistake. So that we got that false once. False. Not to mention there are other mismatches, okay? But to give you an impression, just don't make those mistakes, okay? And there, in the process, you can see how much concept is involved. How much concept is involved. All right, so last four about, it's all about logarithm. It's all about logarithm. Logarithm is actually the place we see a lot of mistake. 22. Okay. 22. We have log base b of a plus b equals to log base b of a plus log base b of capital B. 22, 23. Okay, I'm going to talk about 22, 23 together. Look how intuitive they look, but they are terrible, horrible mistakes. They're terrible, horrible mistakes. So you must, to correct these mistakes once for all thoroughly, I recommend you watch these lessons. Okay, you watch these lessons for more details. Okay, which are properties, common mistake in logarithm. Okay, exponential logarithm properties. You can watch. I think this will be right to the point. All these mistakes are being addressed. Okay, so 1 hour lesson. To make it short, I'm going to go back here. Okay, and just to give you a what is true, what is false. Okay, this is false, but what is true? Okay, I also give you a counterexample. Okay, I also give you a counterexample. What is true is that if you will just change the from addition to multiplication, that will be true. Okay, so what will be true here for the subtraction? Okay, I mean, this is a false. What will make it true? The true one will be if you change it to A divided by B, that will be true. Okay, so if you look at the counter examples, because we're taking calculus class, you rarely use these common bases, and the mistakes show up. Mistakes show up in other forms. Okay, so this mistake often show up in this form, ln, right? And this mistake show up in this form. Because we use ln a lot. ln ln. So when you're about to make that mistake, think of some counterexamples. Think of some counterexample. And be very careful. Okay, this is true. And of course, if you change it to ln, it will be true as well, right? So this is ln natural log, natural log, natural log. And another one would be true because we've been using ln a lot, right? So this is going to be ln, ln, ln. So let's work on the counterexample. A counterexample say I'm going to choose A equals to 1, B equals to E, right? And what's on the right-hand side? The right-hand side, okay, this is 1, this is E. And what would that be? ln 1 is 0. ln E is 1, so that equals to 1 on the right-hand side. What's on the left-hand side? Left-hand side, you're going to have ln 1 plus E. ln 1 plus E, okay, whatever number it equals to is going to be larger than what? Larger than ln E, which is 1, right? Because ln function, natural log function is an increasing function. So when input is larger than that, the output is larger than the output. So the respective output also have the same relationship. Right, so this will be an easy counterexample. I want you guys to really study and you guys really need to do this, okay? Get your hands on, these examples, really study those topics. You have a lot to study. All right, so let's get another counterexample in this case, right? Counterexample. You can come up with your own counterexample, really, okay? So actually, I'm going to use the same, I'm going to use A equals to E because we have to make sure it's in the domain, okay? And B equals to 1. So the right-hand side equals what? Right-hand side is going to be ln E minus ln 1. That's equals to 1, right? And the left-hand side equals to ln E minus 1. ln E minus 1 is going to be less than ln E, right? It's increasing function. ln x is an increasing function. So all of these serve as counterexamples. Okay, so that's why they're false. False one's false. Last two. Okay, last two. Well, this lesson is pretty long. I actually don't know how long it has been, but you may like to watch it, just in two sitting. The last one, last two. Okay, 24 and 25. It's just one is more general, one is more special. And there are other forms, okay? We already seen this mistake being played out, okay? So log base B of A over B equals to log base B of A log base B of B. And the other one is in the form of a common log, base 10. Okay, and of course the mistake can show up in different shapes and forms. We actually saw, okay, to dispute number 24 is false. It's pretty easy, we already did it. Here, Okay. Okay, for base E is false. We know this is false. For common log, okay, so refer to number 18. Does that also give us examples for is false? Okay, so when base equals to E, right? We have number 18. It already told us it's false. We have counter examples out there. For common log, you got some quiz questions on these too. For common log, you have, I can give you A equals to say 100, B equals to 10, right? So the left-hand side equals what? 100 divided by 10, right? That equals to log 10. Log 10 equals what? Equals to 1, right? And what's on the right-hand side? The right-hand side, okay, this is 100, and this is 10. Log 100 is 2. 2 divided by 1, log 10 is 1, so that's 2. 1 is not equal to 2, right? So this is a false. We have a counter example. Okay. And of course, that is false. We have one counter example here. And you can come up with many more counter examples. Okay. Counter example for any base is easy. Let me just give you some counter examples to that. It's a horrible mistake. Okay. A equals to B squared. B equals to capital B, lowercase b. And the left-hand side will be this piece, right? So that's B squared. And that's B. Hopefully you also find some patterns, okay? Log base B of B equals 1. And the right-hand side, you have B squared. You can have B here, okay? So you get 2 over 1, right? Equals to 2. False ones. False. So that concluded all the questions that we covered on this entry quiz to calculus. And historically, I think these are common mistakes for ages past. Okay, after all, these mistakes are not summarized by myself. It's actually summarized by the author who wrote the calculus textbook for the past many decades. But anyway, without further ado, this lesson is pretty long. I expect you guys probably need to watch it from time to time. And if you have any questions, please don't hesitate to reach out to me. I'll be more than happy to show you. Okay. But meanwhile, I know you might feel overwhelmed. Okay, if you haven't studied math for a while, jumping in calculus class is a lot of work. Okay, so thank you for watching. Until next time.